Thank you, Nigel. You are, in fact, safe with me today. Lucky you. So as Nigel said, my hope today is to unpack just a few of the concepts that we've been throwing around in the first half and leave you with a sense of how they apply to your business in programmable marketing and the art and science thereof. So because my background is in mathematics, we have to start with an equation. I apologize. And our equation here is that programmatic plus intelligence equals programmable. So in order to give myself some first-hand context about what programmatic versus programmable means, I decided to make a foray into the world of chatterbots. Now, I don't know how many of you recall, back in the 1960s, I didn't exist in the 1960s, but back then, some researchers at MIT invented a chatbot whom they named Eliza, and they trained her to be a Rogerian psychotherapist. And so you can have conversations with her and she'll respond. And so I went to have a conversation with her. I said, "Eliza, what do you think about Brexit?" She says, "We were discussing you, not me." Okay, good psychotherapist answer. "What about your political situation?" "Why do you ask?" "Because I want your opinion." "What if you never got my opinion?" "Can you please stay on topic?" "Perhaps you would like to be able to please stay on topic." My point here is that Eliza is an example of programmatic technology. Yes, she's able to respond in real time in an automatic fashion, but I don't think she's really learning. I don't think she's really responding to me or to the context of my questions at all. So fast forward now to a slightly more programmable example, I hope. I'm looking for intelligence here. I found Cleverbot, who was invented in the last 10 years and has been trained by having, they say, over 200 million conversations with real humans. And it learns from each one of those conversations. It picks up new words, new vocabulary. In fact, if you go to the website and type in your question, it has a big warning at the bottom saying, "Use at your own risk." There is no human here, but the AI may introduce some topics you may not want to go into, so it can be a little bit crass. I didn't go there. So we had the same conversation, Cleverbot and I. "Cleverbot, what do you think about Brexit?" "I think about dogs. What about you?" I don't know what to make of this. Now, humans really do change the subject and talk about arbitrary other things. Is this intelligent or not? I don't know. "What about the political situation?" "What do you think about Atlas Shrugged?" "All right, maybe this is on topic. I'm not really sure here." "Can you please stay on topic?" I don't think you can complain about that, considering how many times you've changed the subject without reason. But here's where I got shivers just a little bit. Notice that it didn't give me the same word back. It gave me the concept. It didn't use, unlike Eliza, who used the same phrase on topic, it said, "You've changed the subject," as though it understood what I was talking about. Like, there's something here. It has learned a little bit from humans, from context. Who knows whether it's truly intelligent, although apparently it has passed the Turing test, for those of you who are familiar with that. But maybe this is an example of the programmatic future. For perhaps an even more impressive example of programmable technology, I will once again cite the Amazon Echo and its intelligence, Alexa, which can in fact learn from conversations with people to understand their specific speech patterns, their specific dialects and accents, so that it can respond better in real time. Okay. So now that we've explored a little bit firsthand about programmatic versus programmable, let's dig in. Have to have another equation here. Programmatic, as we all know, is incredibly powerful. What gives it that power? Well, automation, of course, driven by computer technology, but also real-time decisioning. What's that about? Well, it means that it has to have certain input available in real time to be able to put into the automation. And that's all about data. Having a wide amount of data available in real time to make decisions. Even Eliza had that. She had the words that I was giving her to respond to. But this is an incredibly important point, and so I want to belabor it just a little bit. In fact, I think we should borrow a term from computer science, which is expressiveness. In computer science, or in human language, expressiveness means the breadth of ideas that can be communicated in that language. So for data, for algorithms, the expressiveness of the data is basically how many ideas can be communicated in it. And in fact, in an algorithm, that means the wider the amount of data, the more sensitive the algorithm can be to the very subtle differences in input. If you think about what expressiveness means for a human face, say, it might be a very small twitch of the eyebrow or a upturn of the mouth. That's what it means to be expressive. And the same concept applies when you're speaking about data and algorithms. So we'll come back to that. But now, what is it about programmable on top of programmatic that's so much more powerful? Well, as we said, it's intelligence. What is intelligence? Well, it's this ability to learn from the input, from the data. So now, let's talk about learning. You might think it's a little bit metaphysical. Obviously, we don't know exactly how we ourselves learn in our brains, and we watch our children learning. But in terms of programmable technology, it all really boils down to basic building blocks of machine learning. There are two fundamental types of machine learning, and I'm going to give you a quick crash course in them, so hang on tight, this will be exciting. The two types are supervised or unsupervised. We'll start with supervised. Supervised learning is when you start with a set of data, and each data point essentially has an answer. That's what makes it supervised. Like a yes or a no, this was good or it was bad. It led to something, it had a certain price tag associated with it. So in a marketing context, it might be this person bought something, this person didn't buy something, etc. And the whole point of supervised learning is that you start with your data, learn from it, and then make predictions about future data for which you don't have the answer. So let's look at what this looks like in practice. A very simple example. Suppose you're looking at a housing market, and you have some data points about the number of bedrooms of a home and how much it sold for. Okay? So on my slide here, I believe I have 7 different homes that sold for different prices, and they had different numbers of bedrooms. This is your historical data. Now, an important part of supervised learning then is fitting a model. What does this mean? You want to have some way of capturing the trend in this data. So let's say that we think there's a linear or a line pattern in this data. We can guess at it. This would be the average home price. We'll just say that's the trend. Now, is this a good fit to my data? Is this a good model? How do we know? Well, what we do here, and basically all supervised learning techniques boil down to this in some sense, is we measure the error. What's the error? It's the difference between the historical data points and the predicted data points, that is, the model itself. So I'm representing the error here by these red lines. Now, is this a good model or a bad model? I don't know. But what I can do is I can add up all of those red bars, or to be more precise, the squares of all of those red bars. I have to be mathematical here. And we can look at that value. And then we do something sort of analogous to the game you play with children where you hide an object and say, warmer, warmer, colder, colder, as they go around the room trying to find it. We adjust our line, looking for smaller and smaller error until we find one that has the smallest possible error. That's it. That's fitting a model. Now, what does this apply? What does this mean for algorithms? What is an algorithm then? Well, an algorithm is you take this model that you've just fit, right? Get rid of your historical data. And now you're going to use this model to predict future home prices. So suppose a new home comes on the market with some number of bedrooms. We now read off of our model its home price, right? So it just makes a prediction based on our model. Different one, different prediction. This is the core concept of all supervised learning. Now, there are many different types of supervised learning, for instance. Linear regression is maybe the simplest example, which is why I'm using it to illustrate. Another relatively common one is called decision trees. So here, instead of fitting your data with a line, you can fit it with lots of different lines. Or if you have lots of different input variables, it becomes more complex than that. But the same concept applies. You're going to minimize your error to get the best fit, and then use your model to make predictions. Now, as some of you may know, the AppNexus programmable bidder has the capability to input decision trees and use them to compute bid prices or bid modifiers in real time. And an even more common one for my world and my context is one known as logistic regression. What's cool about this is that here are your answers to your data. In the first example, it was home prices, but here it can be a yes-no, a Boolean, if you will. So for instance, did the house sell within 1 month? Yes or no? You have some data points. No's on the bottom, yeses on the top. How do you fit this? Well, once again, you can fit it with a certain shape. Here it's not a line, here it's a sigmoid function. Look at those errors, find the one that fits best, and again, use it to predict. And this time you're predicting a probability. Given an input, what's the probability that it will have that outcome? Right? This is incredibly powerful for predicting marketing outcomes, like will a user buy a product, for instance? Yes, no. And in fact, yesterday at our Optimize event, we announced that the AppNexus programmable bidder will soon be able to input custom logistic regression models as well to compute probabilities, evaluations of impressions. Okay. So there are many other different flavors of supervised learning, but I hope by now you understand that the core concept is just to fit some data, use that to make predictions in the future, and that's your algorithm. But I want to give one more example here, and that is deep learning. Because I feel like deep learning sometimes gets alluded to as this like metaphysical, mystical, exciting thing, and it is really cool, I'll give you that. But at its core, it's actually something pretty concrete. So let's talk about it for a moment. Deep learning usually refers to something called deep artificial neural networks, which is something that researchers came up with to try to model some of the ways that synapses interact in the brain, but it's artificial. And the idea here is it's still a supervised learning problem. On the left of this graph, you see some inputs. Those are your starting variables, like your home price, and an output on the right side, which would be, say, your home price, or the bedrooms, I guess, on the left, and home price on the right. And in the middle is where it does something complicated. But all that it is really is layering up together a whole bunch of building blocks of, most commonly, logistic regression. It's adding in a whole bunch of complex layers that are really just these fundamental building blocks that I already showed you. Now, a couple of notes here. One is, one of the things that makes deep learning so powerful, actually, is that it is highly expressive. Because even in my picture, I have only 3 inputs, so 3 variables, but the hidden layers create a whole bunch of extra hidden variables, making it much more expressive. And we already said that expressiveness is the key to having powerful algorithms. But on the other hand, it's very opaque. That is to say, there's a lot going under the hood that you can't really see if you're using this technology. So for our purposes, for marketing, I think we're a long way from it being really the way we want to go. But I just wanted to show you that even deep learning is something at its heart simple. Okay. So we've talked about supervised learning. What about unsupervised learning? Once again, we start with a whole bunch of historical data, say, or data of some kind. But here we don't have a yes-no answer or an outcome associated with it. It's just data. What do you do with it? Well, you look for patterns in it. What are the interesting patterns, clusters, groups, relationships that you can see in the data? You don't know whether they're right or wrong. It's sort of in the eye of the beholder. So for example, let me show you emoji space. This is not all of them, but it's many, many different emojis. What are the patterns in emoji space? What might you want to look at here? Well, researchers at Instagram looked at the patterns of usage, how people use emojis together when they're commenting or chatting or whatever. So what they do is they take every single emoji, right? And you can list out all the different attributes of them, suppose, right? The color, the shape, the content, right? Now imagine that you find a distance metric measuring the difference between those 2 attributes. And now you have sort of a geometry problem. How close are they together in this distance? You can look at different clusters. So the Instagram one had to do with usage. That was what the attribute that they looked at, and they came up with this map. A geometric representation of the patterns of usage of emojis. Now, I think this is kind of interesting. I couldn't really see anything that made a lot of sense to me here other than you see sort of some food and fruit guys over on the west. You see some faces in the middle, a little clock cluster up in the upper right. Who knows what this means? But the point is, it's valid patterns in the data that may be useful for something. But it's not right or wrong. There are other ways to do this. Here's another example of clustering emoji space. A couple of different attributes used here, the color and the type of the emoji. So we have blue up at the top, we have faces down in the lower right, we have clocks again kind of in the middle. Here, this is a very visual, sort of graphic way of grouping the emojis, less dependent on their actual usage. So what's the point here? Unsupervised learning is obviously something that computers can do automatically. Data scientists can do it as long as you've defined this distance metric between your data points. But how do you know what's a reasonable thing to do? Well, humans in the marketing space have been doing this for decades. If you think about what marketers do, you're looking at humans, you're looking at demographics and interests, gender, age, all kinds of things, and looking for the relevant patterns for getting your message to that person and whether or not they'll respond. It is absolutely an art. And while data scientists can do it, humans absolutely can do it better, and they have to do it together. So that is why I believe that programmable is science plus art. Computers can obviously predict based on historical trends, but they need to know what inputs are. This is where that expressiveness point from earlier is so powerful. Algorithms, the programmable future, is only as powerful as the data that goes in. That data going in can be some of these clusters that humans or humans and machines together find in the data, the unsupervised learning problem. Feeding in that information, that expressiveness to supervised learning machines, supervised learning techniques gives the best possible results. So now finally, let me riff on the concept of deep learning. And let's talk instead about depth perception. If you think about how depth perception works, it's bifocal vision, right? Looking at the same object from two slightly different angles together forms that sense of depth. You see the full image. So I submit to you that art of unsupervised learning and human marketing, plus the science of machine learning, gives you programmable. And now let me just leave you with what Cleverbot thinks about that. What do you think about machine learning in the era of programmable age? I think that in the properly controlled environments handled by competent people, it can be quite advantageous. Thank you, Cleverbot.